The light, arriving from Andromeda tonight, began its crossing about 2,482,000 years ago. That distance already destroys any human idea of nearby. Andromeda is close by the standards of large galaxies, yet the fastest thing in nature needs nearly 2.5 million years to reach the solar system from its center. The visible galaxy is therefore not Andromeda at the same moment as Earth. It is Andromeda from a time long before Homo sapiens existed. Any supernova detected in that arriving light happened before recorded history by an interval that dwarfs recorded history. Whatever is occurring in that galaxy at this instant cannot be known here until another 2.5 million years have passed. The distance is not merely a length, it is a delay built into every possible exchange of information. Even the word now splits apart across the gap. Now at Earth can be defined by local clocks. Now at Andromeda depends on a chosen frame and cannot be inspected from here. Astronomy can reconstruct a past state from arriving light, compare motions, and predict possible futures. It cannot remove the travel time that separates cause from knowledge. The nearest large spiral beyond the Milky Way is close enough to study in detail and too distant to share a common present through observation. No existing human technology can turn that distance into a practical journey. Even a craft moving at 1/10 the speed of light, with acceleration, deceleration, fuel, shielding, and survival all granted, would need about 24,820,000 years in the frame of the galaxies. Relativity would reduce the time aboard by only about 124,000 years. The travelers would still face almost 24,700,000 years. That is not a voyage in any human sense. It is a migration, longer than the existence of the human species. Repeated many times over, languages could appear and vanish. Continents could shift. Entire branches of life could rise, divide, and disappear before the destination grew near. At the speed of light itself, a simple reply to a message would take roughly 5 million years to return, even if the answer were sent at once. The distance is worse than the number suggests, because the parts of a galaxy that control its future continue far beyond the last visible stars. Their most diffuse gaseous outskirts may already overlap, even while the bright stellar disks remain separated by an enormous abyss. Andromeda looks almost manageable from Earth. Under a dark sky, it can appear as a pale streak, a small disturbance in the night. A long exposure reveals a grand spiral, tilted toward the Milky Way, with a brilliant center and sweeping lanes of dust. Its bright disk spans roughly 6 times the apparent width of the full moon, yet distance compresses that enormous structure into a quiet patch of light. 6 lunar widths correspond to about 3 degrees across the sky. At Andromeda's distance, that angle represents roughly 130,000 light-years across the bright stellar structure. The faint smudge is wider than the Milky Way's commonly pictured stellar disk. The familiar picture encourages a clean division. Here is the Milky Way. There is Andromeda. Between them lies black space. The stars appear to stop, so the galaxy appears to stop with them. But starlight marks only the easiest part to see. The bright disk is where stars are crowded closely enough to draw a visible shape. It is not a wall. Beyond the spiral arms, stars become sparse. Farther out, ancient stars and globular clusters continue through a much larger stellar halo. Dark matter reaches farther still, shaping the motions of objects that can be seen without revealing itself directly. Gas also extends outward, but it becomes so thin and so highly ionized that it nearly disappears from ordinary images. This gas is called the circumgalactic medium. It surrounds a galaxy, moves through its gravitational field, receives material expelled by dying stars, and can supply material that may eventually move inward. It is not the same as the dense gas between stars and the bright disk. It is a vast, diffuse atmosphere around the visible galaxy, although even the word atmosphere can mislead. There is no surface below it, and no clean top above it. Near the disk, the gas has been disturbed by generations of stellar activity. Massive stars pour radiation into their surroundings. Supernova explosions drive shocks and carry newly forged elements outward. Streams from smaller galaxies can be torn loose by gravity and pressure. Gas falling toward the galaxy meets gas moving away from it. The result is not a smooth shell. It is a changing mixture of temperatures, densities, chemical histories, and velocities. Farther from the disk, the medium becomes quieter, but not irrelevant. Its particles are separated by distances that would make any terrestrial vacuum seem crowded by comparison. Suppose a spacecraft crossed that region. Through its window, the gas would have no visible outline, yet spread across hundreds of thousands of light years, a tiny amount of material along each stretch of space can add up to a major reservoir. That reservoir matters because galaxies cannot live on stars alone. New stars require gas. Heavy elements made inside stars do not remain confined to the places where they formed. Explosions and winds move them outward. Gravity can draw some material back. Passing satellites can stir, compress, or strip it. The outer gas therefore connects a galaxy's past activity to its possible future. What looks like a border is actually a working region. The problem is that diffuse ionized gas is exceptionally hard to see. A bright nebula inside a galaxy can announce itself by glowing. The remote halo is too thin to do that strongly across most of its volume. Looking directly at it is like asking a nearly transparent substance to identify itself against darkness. Project absorption maps in the gas of Andromeda, known as Omega, approach the problem from the other direction. Instead of waiting for Andromeda's halo to glow, the project used bright objects far behind it as backlights. Those objects were quasars. A quasar is the intensely luminous center of a distant galaxy, powered by matter falling toward a supermassive black hole. The black hole itself does not shine, but the material around it can become hot enough to radiate across enormous distances. From Earth, a quasar can look like a point. Its light may have traveled for billions of years before reaching the region around Andromeda. The project assembled 43 quasar sightlines passing at different projected distances from Andromeda's center. Each quasar supplied a narrow beam through a different part of the surrounding space. Together, the beams turned the halo into something that could be sampled across a wide area. They did not produce a conventional picture. They produced a map built from missing light. That method works because atoms and ions absorb particular wavelengths. When quasar light passes through the circumgalactic gas, carbon, silicon, and oxygen remove narrow bands of ultraviolet light according to their atomic structure. A spectrograph separates the surviving light by wavelength. The resulting dark features reveal which ions were along the path. An ion is an atom that has lost or gained electrons. Radiation, collisions, and temperature determine which ionization states can persist. Silicon, missing 2 electrons, traces conditions different from oxygen missing 5. No single ion reveals the entire halo. Each responds to a limited range of physical conditions, so several ions are needed to uncover gas that is cooler, warmer, denser, or more diffuse. What appears to be one transparent volume can contain phases that barely interact in the same way with incoming light. Absorption has a peculiar advantage. The gas does not need to be bright. It only needs to stand between the telescope and something brighter. A small number of ions along a very long path can leave a measurable line even when their own emission would be hopelessly faint. The quasar supplies the light. The intervening gas removes particular wavelengths. Hubble recorded the carbon and silicon diagnostics, while archival far ultraviolet spectroscopic explorer spectra supplied the highly ionized oxygen measurements. The positions of those features also reveal motion. Gas moving toward or away from the telescope shifts the wavelengths it absorbs. That shift helps separate material associated with Andromeda from gas closer to the Milky Way and from other structures along the line of sight. The strength and pattern of the absorption give clues to the amount of material, its ionization, and the phases of gas sharing the same region. Ultraviolet observations were essential. Earth's atmosphere blocks much of that light, which protects life at the surface but prevents the needed measurements from the ground. Hubble's cosmic origins spectrograph could examine the quasar light above the atmosphere and resolve the carbon and silicon marks impressed on it during the crossing. Archival observations from the Far Ultraviolet Spectroscopic Explorer provided useful oxygen coverage for a smaller group of targets. The 43 beams pierced projected distances ranging from about 25 kiloparsecs to 569 kiloparsecs from Andromeda's center. 1 kiloparsec is more than 3,200 light-years. The farthest sample, therefore, lay almost 1,900,000 light-years from the center in projection. Projected distance needs care. It is the apparent separation across the sky, translated into physical scale at Andromeda. A beam that appears 569 kiloparsecs from the center does not reveal the exact depth of every absorber along that path. The measurement is a slice through a three-dimensional environment, not a pin fixed to a solid shell. The geometry leaves room for uncertainty about which remote gas belongs to Andromeda and which belongs to the wider local group. Even with that caution, the pattern was extraordinary. The full survey traced ionized material across a region vastly larger than the bright spiral. Silicon in a particular ionized state covered nearly every sampled direction out to more than the commonly adopted virial radius. Adequate measurements of more highly ionized oxygen came from archival spectra for 11 of the targets. Within that smaller subset, oxygen had a near-unity covering factor to roughly 1.9 times the virial radius. The virial radius is not an observed skin. For this study, Andromeda's virial radius was roughly 300 kiloparsecs. It marks a model density scale in the dark matter halo, not a physical surface. Change the assumptions about the galaxy's mass or the chosen definition, and the number changes. Crossing that radius does not produce a flash, a shock, or a sign saying that the galaxy has ended. The absorption also changed with distance. The inner circumgalactic region was more complicated. Multiple gas components appeared along many paths. Lower and higher ionization states shared the environment, suggesting several temperatures and densities shaped by activity nearer the disk. Farther out, the pattern became smoother. Highly ionized gas occupied a broader region than the cooler phases traced by lower ions. That layered behavior carries a history. The inner halo is close enough to feel the direct effects of the galaxy's star-forming disk. Supernova-driven material can enrich it with elements heavier than hydrogen and helium. Infalling gas can meet those outflows. Satellite debris can add another current. The outer halo is more diffuse and more highly ionized, so the chemical traces vary more gently across the sampled directions. None of this means that the space around Andromeda is dense. It means the opposite lesson has been taken too far. Thin is not the same as absent. A single cubic region may hold almost nothing, while an envelope hundreds of thousands of light-years deep contains enough matter to influence how a galaxy receives fuel, loses material, and responds to its surroundings. The Omega measurements estimated that the warm and cooler ionized phases inside the virial radius contain tens of billions of times the mass of the Sun in ordinary matter, with the exact total depending strongly on the assumed abundance of heavy elements. That uncertainty is important. Absorption from metals reveals metal ions directly, but converting those detections into the total mass of mostly hydrogen gas requires a model of ionization and metallicity. Even the uncertainty is revealing. If the gas contains fewer heavy elements per unit mass, more total gas is needed to create the observed absorption. If it is richer in heavy elements, less gas is required. Either way, the halo is not decorative mist around a completed galaxy. It is part of the material cycle that helps determine whether gas can cool, fall inward, form stars, or remain suspended in a hotter phase. That changes the meaning of the distance to Andromeda. The standard figure measures from the solar system to the galaxy's center. It does not measure from one final piece of the Milky Way to one first piece of Andromeda, because neither final piece is easy to define. The bright disks are separated by an abyss. The extended environments are not separated in the same clean way. Andromeda's center is about 761 kiloparsecs away. If its circumgalactic material can be traced to a projected distance of 569 kiloparsecs in some directions, then the outer reach being sampled is a substantial fraction of the entire center-to-center distance. The arithmetic is simple. The interpretation is not. The Milky Way also has a circumgalactic medium. It is harder to map from Earth because the solar system sits inside the galaxy and inside its extended environment. Every direction begins within the foreground that astronomers are trying to measure. Separating nearby gas, distant halo gas, satellite streams, and any more diffuse local group or intergalactic contribution becomes a problem of velocity, chemistry, geometry, and modeling. Andromeda offers the external view that the Milky Way cannot provide for itself. The two galaxies have broadly similar scale and structure, so Andromeda's immense halo suggests that the Milky Way's halo may also extend far into the space between them. If both warm and hot gaseous envelopes reach comparable distances, their most diffuse outer regions may overlap. That word "may" is doing essential work. The 43 quasar beams did not draw a continuous boundary around Andromeda. They sampled selected paths. The outermost paths are vulnerable to confusion, with gas belonging to the local group rather than exclusively to one galaxy. The Milky Way's own halo is difficult to measure from within. Temperature matters too, because different ions reveal different phases. A halo traced by warm oxygen does not have to share the same boundary as cooler silicon-bearing gas, hot X-ray emitting plasma, dark matter, or stars. There is therefore no justified claim that two sharply bounded objects have begun a direct encounter. There are no sharply bounded objects at this scale. There is evidence that Andromeda's ionized environment extends astonishingly far. There is evidence that the Milky Way possesses its own extended gaseous environment. From their measured scales and their relatively small separation, scientists infer that the warm and hot outer media may already meet or blend somewhere between the galaxies. The famous gap between the Milky Way and Andromeda may not be a pristine interval waiting for a future encounter. Long before their stellar disks approach each other, the galaxies can share a thin, difficult-to-assign medium of ionized matter. Their centers remain nearly 2.5 million light-years apart. Their stars remain overwhelmingly isolated, yet the quietest outskirts may have no empty lane between them. If this changed the way the gap between galaxies feels, subscribe and help me keep tracing the matter hidden beyond their stars. That possible overlap creates a problem of ownership. Once diffuse gas lies in a region influenced by both galaxies, the question of which galaxy it belongs to may have no single physical answer. Astronomers can compare its velocity with the motion of Andromeda, the Milky Way, and nearby satellite systems. They can measure chemical abundance and ionization. They can model the gravitational field. None of those tests creates a rigid border where nature has not supplied one. Gas can be associated more strongly with Andromeda in one phase and with the wider local group in another. A cool cloud might move through a hotter shared medium. Material stripped from a small satellite might carry a chemical history, unlike the plasma around it. Two components at different temperatures can occupy the same general volume while responding differently to pressure, radiation, and gravity. This makes the space between galaxies active without making it crowded. A particle can travel immense distances before striking another particle, yet the gas as a whole can still exert pressure. A small galaxy moving through it can lose gas when the surrounding medium pushes against its own reservoir. A cloud can slow through drag. A hotter phase can confine a cooler cloud. Turbulence can mix metals across boundaries that looked obvious in visible light. Pressure in such a medium does not require particles to be packed together like air near Earth's surface. It emerges from countless rare interactions spread over astronomical distances and times. A force too weak to notice across a human lifetime can steadily reshape a cloud over millions of years. Gravity is similarly patient. The field from each large galaxy acts across the shared region, while the gas responds according to its position, velocity, temperature, and density. The result is a slow competition, without a line where one influence simply turns off. The consequences reach back into the galaxies. Star formation depends on whether gas can arrive at a disk in a cool enough state. Feedback depends on whether material launched outward escapes, stalls, mixes, or returns. Satellite galaxies depend on whether their gas survives passage through the larger halo. Chemical evolution depends on how metals are carried away and diluted. The circumgalactic medium is where all of those paths cross, but the outer gas does not need to wait for the bright disks. If the Milky Way and Andromeda gaseous halos overlap, pressure forces and mixing could begin while their stellar disks remain far apart. Shocks in the overlap region have not been directly detected. If the galaxies later undergo a close encounter, its earliest interactions would be expected in diffuse material, rather than through collisions between individual stars. Such an encounter remains possible rather than inevitable. That distinction prevents a dramatic finding from becoming a false one. Possible halo overlap is not the same as a direct encounter between the bright galaxies. Such a claim would hide every uncertainty that makes the result scientifically interesting. It would turn gradual, phase-dependent contact into a single event. It would confuse an inferred meeting of tenuous gas with the much later transformation of stellar disks. The more accurate picture is stranger. A galaxy fades outward through several different components. The bright disk gives way to sparse stars. Dark matter shapes a much larger gravitational domain. Cool, warm, and hot gas occupy different ranges and reveal themselves through different measurements. Satellites and stripped streams pass through the same territory. Farther out, absorption assigned to the circumgalactic medium becomes difficult to distinguish from gas that may belong to a more diffuse local group component or the surrounding intergalactic medium. Distance remains real through all of it. A beam of light still needs about 2,482,000 years to travel from Andromeda's center. A hypothetical craft at 1/10 light speed still faces almost 25 million years. No extension of the halo makes the stellar gulf easy to cross. The discovery makes the gulf harder to define, not easier to traverse. That is why the distance between galaxies is worse than it first appears. It is simultaneously too large for human travel and too physically connected for the word empty. The number from center to center is precise enough to print, but the distance from edge to edge depends on which edge is meant. Stars, gas, dark matter, gravitational influence, and group membership do not end together. A galaxy has no single hard edge, and the space between the two is a shared physical system. Beyond the stellar disk, dark matter and baryonic plasma follow very different distributions. Both are largely invisible. Both help shape the space between the Milky Way and Andromeda. Their invisibility comes from different physics, and that difference controls what each can reveal. Dark matter supplies most of the mass surrounding a large galaxy. It does not shine, and ordinary light passes through it with almost no effect. Its presence emerges through gravity, through the speeds of stars and gas, through the motions of satellite galaxies, and through the bending of light from more distant objects. A dark matter halo can reach far beyond a bright spiral disk. Its outer boundary depends on whether the definition follows density, orbital history, or gravitational influence. Baryonic matter is the familiar matter made from protons and neutrons, accompanied by electrons. Stars, planets, dust, and living chemistry all belong to this category. Beyond a galaxy's bright body, much of that matter becomes plasma. Atomic nuclei move through a sea of free electrons. The plasma can absorb, scatter, and emit electromagnetic radiation because its particles carry electric charge. Yet its density can be so low that those effects remain almost impossible to see in an image. The distinction changes the picture immediately. A region dominated by dark matter is a gravitational structure. A region filled with baryonic plasma is also a physical medium, even when it produces no visible glow. Their outer distributions can overlap without sharing the same shape, temperature, or boundary. So the corridor cannot be represented by a single pair of transparent spheres. It contains superposed structures whose distributions answer different questions. The most elusive baryons did not become exotic. They became thin, hot, and highly ionized. Much of the diffuse gas outside galaxies occupies densities below roughly 1/1000th of a particle per cubic centimeter. Its neutral fraction can fall below 1 part in 10,000. Hydrogen that has lost its electron no longer produces the strong neutral hydrogen signal that reveals colder clouds. The dominant material can therefore be present, while the most familiar tracer has almost vanished. Low density also defeats direct imaging. Many forms of plasma emission depend on encounters between particles. When density falls by a factor of 10, the resulting glow can fall by about a factor of 100. A very long column of gas may contain substantial mass, while every small volume radiates feebly. Gas at hundreds of thousands or millions of degrees can remain visually black because temperature measures the energy of individual particles, while brightness also depends on how many particles are present and how often they collide. Absorption offers another route, but it introduces its own filters. A useful absorption line requires a bright source behind the gas. It also requires an ion in the correct state. Highly ionized oxygen, silicon, and carbon reveal selected temperature and ionization ranges. Converting those traces into a total gas mass depends on the abundance of heavy elements, the strength of the surrounding radiation, and the thermal history of the plasma. A large reservoir of hydrogen can hide behind a small and uncertain amount of a chosen ion. Even geometry becomes difficult. A faint detection along one narrow beam gives an electron or ion column through the entire path. It does not automatically reveal where along that path the material sits. Bright galaxies appear compact because cooled matter announces itself efficiently, while their diffuse baryonic outskirts demand indirect methods and careful assumptions. Absorption transformed the apparent edge of a galaxy, but it could not by itself determine where most ordinary matter in the late universe resides. Metal lines favor gas, containing measurable heavy elements. Different ions favor different temperatures. Bright background sources sample selected directions. A method built from those detections can reveal structure beautifully while still missing gas that is too hot, too metal poor, or in the wrong ionization state. The larger problem began with a comparison across cosmic time. Conditions in the early universe constrain the total abundance of baryonic matter. The patterns in ancient radiation and the production of light atomic nuclei point to a consistent amount. Later observations could identify only a minority in stars, cold gas, and the bright interstellar media of galaxies. The rest had to remain somewhere in ordinary form, because baryons do not simply turn into dark matter. Expansion, heating, and ionization could make them difficult to locate without removing them from the universe. That problem required a tracer shared by nearly every ionized phase. Free electrons provide such a tracer. Their response to a radio wave does not require heavy elements. It does not depend strongly on whether the surrounding gas is warm or extremely hot. Every ionized hydrogen atom contributes an electron, and helium contributes more when fully stripped. The ideal probe therefore needed to cross cosmological distances, retain precise timing across a wide band of radio frequencies, and originate at a known distance. Fast radio bursts supplied that combination. Their frequency sweeps measure integrated free electrons along entire cosmic paths. That opened a route from isolated halo detections to the distribution of baryons across a cosmic population. A fast radio burst is an intense pulse of radio emission that can last only a few thousandths of a second. Many originate in galaxies hundreds of millions or billions of light years away. The pulse spans a range of radio frequencies. During its journey, free electrons in diffuse plasma alter the speed at which those frequencies propagate. Higher radio frequencies arrive first, lower frequencies arrive later. The delay grows rapidly toward lower frequency, following the inverse square of frequency. That distinctive sweep is measurable with great precision. It differs from a simple late start at the source, because every part of the burst follows the same plasma relation across the observing band. The size of the delay gives the dispersion measure. That quantity is the integrated number of free electrons along the path. A dense region over a short distance can add dispersion. So can a very thin medium spread across an enormous distance. The measurement does not require the plasma to glow, and it does not require any particular metal. It responds directly to the electrons carried by ionized ordinary matter. Dispersion alone still leaves an ambiguity. A large value might come from a distant path through modest density, a nearer path through dense structures, or a complicated environment around the burst. Distance is therefore essential. Once the source galaxy and its redshift are known, the observed electron column can be compared with the length and cosmic epoch of the journey. The burst carries a running measure of the free electrons along the whole route, including matter too faint for conventional imaging. It constrains the total column accumulated across all ionized regions rather than isolating each region by itself. The decisive test required many bursts whose source galaxies were known. The sample contained 69 fast radio bursts localized to host galaxies. 39 were discovered by the Deep Synoptic Array, while 30 came from other radio facilities. The array combined signals from many antennas to determine precise positions on the sky. Optical and infrared observations then identified likely host galaxies, and spectroscopy measured their redshifts. Those steps transformed a burst with an electron column into a burst with both an electron column and a cosmological distance. Localization mattered because a dispersion measure without a host is underdetermined. An assumed relation between dispersion and distance would risk building the desired answer into the method. A measured redshift provides an independent distance coordinate. Bursts at different redshifts then test how dispersion grows as paths become longer and pass through more cosmic structure. The sample also avoided dependence on a single telescope or a single class of host. It included nearby sources and sources beyond a redshift of 1. Some paths crossed relatively quiet regions. Others intersected galaxy halos or clusters. Some bursts carried substantial local dispersion from their host galaxies. That diversity was a complication for any individual event, yet it became useful across the population because different components shape the distribution in different ways. The arrival sweep measured total dispersion. An electron map estimated the Milky Way foreground, Host spectroscopy fixed the redshift, and simulated cosmic paths described intervening structure. One burst could not reveal the whole distribution of baryons. 69 independent paths could constrain it statistically. The experiment was no longer a collection of spectacular pulses. It became an ensemble of known path lengths through different realizations of the cosmic web. With 69 paths, components that overlap in one burst began to separate statistically across the population. Each burst crossed the Milky Way disk and halo, entered the cosmic web, sometimes pierced other halos, and finally emerged from plasma near its host galaxy. Every region added free electrons to the same measured dispersion. A single foreground estimate could never solve that mixture. The Milky Way contribution varies with direction. Host galaxies differ in mass, orientation, star formation, and the location of the burst within them. Intervening halos occur irregularly. The intergalactic medium itself forms clumps, filaments, sheets, and underdense regions. Two bursts at the same redshift can therefore have very different dispersion measures without either measurement being wrong. Cosmological expansion changes the observed host contribution as well. A fixed electron column near a distant source produces a smaller observed dispersion contribution than the same column nearby. The host term needed a broad distribution that evolved correctly with redshift. Exceptional source environments could populate its high end. Sightlines that pierced a halo also tended to cross denser parts of the cosmic web, so the simulations preserved that connection. Treating the regions as independent would place too much confidence in a false separation. This is the central difficulty of the method. Dispersion measures total free electron column, while the scientific question asks where those electrons reside. Only the full spread of measurements across distance could reveal which cosmic arrangement produced them. The intergalactic medium and intervening halos leave different statistical signatures. Diffuse intergalactic gas appears on almost every long path, and its average contribution rises with redshift. Dense halo encounters occur irregularly and create a more asymmetric spread of measurements. Host galaxies add another broad contribution whose observed strength changes with distance. Simulated rays preserved the relationship between halos and overdense parts of the cosmic web. 69 localized bursts. Then let the full spread of dispersion values test different divisions of ordinary matter, including variation in the host galaxies. No individual pulse revealed where every electron sat. The population revealed which cosmic arrangement could produce them all. Tests with different source selections and alternative treatments checked whether a few unusual bursts controlled the result. The average dispersion constrained the total diffuse ionized content, while the scatter carried information about location. The result remained statistical, with honest uncertainty, and could not be treated as a map of any chosen local corridor. The preferred analysis placed roughly 76% of ordinary matter in intergalactic space and about 15% in the halos intersected by the bursts. Each estimate carried an uncertainty of roughly 10 percentage points. Stars, cold neutral gas, and other condensed components occupied the remaining fraction, but the largest reservoir remained outside virialized halos. The inferred total abundance of baryons in the late universe agreed with the amount expected from early universe measurements. That agreement matters because the radio method follows free electrons across a much later cosmos, and uses entirely different physical information. The ordinary matter had not disappeared. It had become diffuse and ionized across structures that emit too weakly to dominate conventional images. The result also separated baryons from dark matter in a new way. Dark matter is more concentrated in collapsed halos than ordinary matter is. Gravity draws both components toward structure. Gas can also heat, collide, radiate, and receive energy from stars and black holes. Those additional processes allow baryons to migrate relative to the dark matter framework. That reverses the familiar visual hierarchy. Galaxies are the brightest concentrations, yet they are not the main spatial home of ordinary matter. Across the late universe, diffuse regions outside halos contain far more baryonic matter than stars and cold gas inside galaxies. The displaced matter also points toward efficient feedback. Gas falls into dark matter halos as galaxies grow. Some of it cools and forms stars. Massive stars then release radiation, winds, and supernova explosions. Accreting black holes can drive still more powerful outflows. These processes return energy and momentum to surrounding gas. In smaller halos, heated gas can move far beyond the bright galaxy, and sometimes beyond a conventional virial boundary. In larger groups and clusters, deeper gravity retains more hot plasma, though it may still redistribute that plasma toward great radii. Outflows also carry heavy elements created in stars. Metals detected far from galaxies therefore reveal that baryonic matter has been transported as well as heated. A high intergalactic fraction is consistent with a universe where feedback has depleted many galaxy halos and enriched the wider cosmic web. The radio result does not identify which explosion moved each parcel of gas, and it does not make every feedback model equally successful. It sets a strong population constraint. Any model of galaxy formation must place most ordinary matter outside viralized halos by the late universe, while still producing the observed stars and galaxies. That requirement reaches beyond galaxy evolution. Moving gas outward changes the distribution of total matter on cosmic scales. Dark matter still dominates the mass, but strong feedback can smooth ordinary matter around halos enough to weaken some small-scale clustering signals used in precision lensing studies. Intergalactic space therefore preserves a history of ejection, heating, mixing, and reaccretion. It carries the effects of stellar death and black hole growth long after the bright events have faded. Intergalactic matter does not spread as a perfectly uniform mist. Gravity builds a cosmic web of filaments, sheets, knots, and voids. Gas follows that framework, then pressure, shocks, radiation, and feedback modify its final distribution. Some remains relatively cool and photoionized. Some is shock-heated to hundreds of thousands or millions of degrees. The warm and hot phases can hold substantial mass while producing little visible emission. Long cosmological sightlines usually cross many filaments. Even a path through underdense regions accumulates free electrons over enough distance. Voids therefore mean lower density, not absolute absence. At the other extreme, a foreground group or cluster can add a concentrated electron column. The dispersion distribution combines all of these environments. The web should not be imagined as bright smoke. Its particles are separated by enormous distances on laboratory scales. A high temperature describes the motion of individual particles. It does not guarantee strong heating of an object passing through, because collisions would be exceedingly rare. Most of the journey between galaxies would still look black to unaided eyes. Electron density rises through filaments and halo outskirts, falls through voids, and changes again around dwarf galaxies and groups. The unseen route has structure at every scale, while dispersion reveals only the accumulated free electrons across it. Those halos sit inside a larger, structured baryonic network, shaped by both gravity and feedback. Intergalactic distance, therefore, describes passage through changing physical environments, even when no visible landmark announces the transitions. That cosmic result cannot be pasted directly onto the local group. It does not provide a density profile along the line from the Milky Way to Andromeda. Most of the 69 radio paths crossed far greater distances and sampled many unrelated structures. Their combined dispersions reveal the typical division of baryons across the universe, not the precise placement of gas inside the local group. That limitation does not sever the connection. Quasar absorption around Andromeda independently shows ionized gas extending far beyond its bright disk. Milky Way observations and models indicate a similarly broad circumgalactic medium. The cosmic burst population shows that such diffuse plasma belongs to a much larger pattern in which most baryons occupy intergalactic space. Together, those results make a barren corridor implausible. They do not prove a single continuous bridge with a known density. The exact path could pass through Milky Way halo gas, Andromeda halo gas, overlapping warm and hot phases, material associated with dwarf galaxies, a more diffuse local group component, and the surrounding cosmic web. Some of those labels may overlap physically. At great radius, ownership can become less meaningful than temperature, density, velocity, and chemical history. The corridor contains interacting layers of matter, while its detailed three-dimensional structure remains only partly sampled. The evidence supports fading layers of gas, not a solid bridge with a measured edge. The apparent gap between the Milky Way and Andromeda is roughly 2.5 million light-years from bright center to bright center. Part of that distance lies inside extended galactic environments. Part may pass through overlapping gas. The rest may include a more diffuse local group medium and the surrounding cosmic web, but its exact partition is not measured. Dark matter shapes the gravitational terrain across that distance. Baryonic plasma supplies a sparse physical medium whose electrons alter radio propagation. Feedback has carried some of that matter outward from galaxies. Gravity continues to draw the local group together, even as the future orbit of its two largest galaxies remains uncertain. The result is a different meaning of intergalactic. It no longer signifies an interval after one object ends and before another begins. It describes a regime where density falls. Cooling becomes inefficient, boundaries overlap, and most ordinary matter becomes extremely difficult to see. The bright disks remain real and distinct. Their surroundings participate in a continuous hierarchy of halos, filaments, and diffuse structure. Visible galaxies are rare cooled knots inside a larger baryonic web. Gravity still acts across that web, and it is changing the distance itself. Even so, Andromeda is not being pulled close enough to make the distance usable. At 1% of the speed of light, an ideal crossing would last about 248 million years. At Voyager 1's present speed, it would last about 43,800,000,000 years. more than 3 ages of the universe. Those are lower bounds, not mission plans. They ignore acceleration, braking, fuel, shielding, repair, navigation, and the moving target. Voyager 1 is not aimed at Andromeda, and the comparison does not describe its future. It uses a real spacecraft speed to show how little the word fast means when the destination is another galaxy. Relativity does not forbid a massive object from moving at 1% or 10% of light speed. It forbids that object from reaching light speed and makes each further gain increasingly expensive. A journey to Andromeda is allowed by physical law and functionally impossible on human and known technological scales. Andromeda is also not a fixed mark painted onto the sky. A craft would need to aim for the galaxy, as it will be when the craft arrives. While stars, satellites, gas structures, and both large galaxies continue to move. Once the craft had crossed a substantial fraction of the route, corrections from the Milky Way would take millions of years to reach it. Deep time removes timely remote operation and forces the mission to interpret a changing target on its own. More transmission power could strengthen a signal, but it could not shorten the light delay. The most perfect communication system permitted by physics still waits on the distance. The target is not stationary during that wait. Andromeda is currently approaching the Milky Way along the line of sight at about 109 kilometers per second. That motion is real, and it is often compressed into a simple prediction. A present distance is divided by a present approach speed, producing a date for collision. The calculation is tempting because it looks complete. It is not an orbit. The measured approach is only one component of Andromeda's motion. Sideways motion matters. The masses of the Milky Way and Andromeda matter. Their extended dark matter halos matter. The Large Magellanic Cloud and the Triangulum Galaxy can alter the motion of the larger pair. As these bodies move, gravity changes their speeds and bends their paths. The galaxies are not rigid points crossing an empty grid. They are extended, interacting mass distributions inside a small group whose members exchange momentum. That is why the future of the pair has become less certain rather than more certain as measurements improve. Earlier accounts often presented a merger as nearly guaranteed and placed the first major encounter several billion years ahead. A 4-galaxy analysis from 2025 found only a little over a 50% chance that the Milky Way and Andromeda would merge within 10 billion years. In that model, small changes in present motion could separate a direct encounter from a distant passage. A newer 4-galaxy model, published in 2026, used updated Gaia-based proper motions and raised the fiducial merger probability to about 90% within 10 billion years. Among the realizations that merged, the median time was near 6.5 billion years. Across the full 2 standard deviation range of Andromeda's proper motion, the modeled probability still ran from about 65% to 100%. The newest result favors a merger without making it certain. Andromeda's approach does not rescue travel or communication. Whether the galaxies merge, miss, or pass and return, the change unfolds across billions of years. A future gravitational encounter can transform both galaxies without turning the present interval into a route usable by human technology. That orbital uncertainty exposes the same mistaken boundary. The crossing begins inside the Milky Way's extended environment, moves through gas and dark matter whose ownership fades into the wider local group, and enters progressively denser gas around Andromeda. The interval remains extraordinarily thin. A slowly moving craft would encounter something close to vacuum. Volume changes the consequence of that low density. A medium can be too faint to image directly and still hold enormous total mass when it occupies millions of light years. That is why bright galaxies can dominate the view, while most ordinary matter resides beyond them. The wider baryonic web also participates in galactic evolution. Material moves toward halos, cools toward disks, and can return outward through stellar and black hole feedback. If a future close encounter occurs, the extended gas can respond before the stellar disks overlap. The connection is physical, gradual, and conditional. The exact local amount remains unresolved. The measured reach of a circumgalactic medium changes with the ion, density threshold, and geometry used to trace it. Evidence for enormous halos is strong. Their outer interaction is a plausible inference. A precise division among Milky Way gas, Andromeda gas, shared local group material, and an intergalactic filament is not yet available. The map becomes least certain exactly where diffuse ordinary matter occupies most of the volume. Galaxies are easiest to see where matter has cooled into stars, not where their influence ends. The Milky Way and Andromeda are separated by a light delay no engineering can negotiate, yet joined by gravity and possibly by the faint outer phases of their gas. The newest orbital model favors a merger, but the exact path and the ownership of the intervening plasma remain unresolved. The distance between galaxies is therefore not a clean measure from one edge to another. It is the scale of a physical system whose centers remain functionally unreachable on human and known technological scales, while its outer structures become difficult to separate long before the bright disks meet.